Hi everyone, welcome back to my channel. The topic I have included today is Euler's Totient function, which has a deep relationship to prime numbers. And let's start from prime numbers and sail through Euler's Totient function. Before we start with Euler's Totient function, let's recall prime numbers and composite numbers. Prime numbers is an integer greater than 1 and which has no divisor except 1 and the number itself. Suppose if you take the factors of 3, we will get 1 and 3. 1 into 3 and 3 into 1. Only two factors are there. Next one, factors of 5. Here also we will get 1 into 5 and 5 into 1. So we can see that 1 and the number itself are the factors. So these numbers are prime numbers. And then what are composite numbers? An integer n greater than 1 is called composite when at least one of the divisor other than 1 and the number itself exists. For example, if you take the factors of 4, we can say 1 into 4 is 4, 2 into 2 is 4, again 4 into 1 is 4. So we can see that other than 1 and the number, it is having other factor also. Similarly, if you write the factors of 15, so 1 is anyways there, 1 into 15, then 3 into 5, 15, 5 into 3, 15, and 15 itself, the number itself. So here also, we can see that it is having more than 2 factors. That is why they are called composite numbers. We have already studied this fundamental theorem of arithmetic in the 10th grade. Every composite number can be represented as product of prime factors in one and only one way. So if you take number 36, you know that 36 you can factorize by using prime numbers, that is 36 by 2, 18. Again you do by 2, you will get 9. You can divide by 3, again you will get 3, 3 you will get 1. So 36 you can write as 2 into 2 into 3 into 3. Similarly, every composite number we can express as product of prime factors. And now what is unique factorization theorem? Every integer where n is greater than 1 can be expressed uniquely in the form n can be expressed as p1 raised to a1 into p2 raised to a2 etc. pk raised to ak. p1 p2 etc. pk, they are prime numbers, and the condition is p1 less than p2 less than up to pk, and a1 a2 etc. ak are the positive integers. So let us take one example, 240. 240, if you factorize this, we will get 1 by 2. Again you divide by 2, you will get 60. Divided by 2, you will get 30. Again by 2 will get 15. Then divide by 3, you will get 5. And 5, we will get 1. So 240 you can represent as, how many 2's are there? 1, 2, 3, 4. So you write 2 raised to 4. Into how many 3's are there? Only 1 3. So 3 raised to 1. Into 5 raised to 1. So P1, P2, P3, that is 2, 3 and 5 are primes and they represent P1, P2 etc. And what about A1, A2? They are the powers and they are positive integer. So this is how you represent a number using unique factorization theorem. Another most common term we come across while we are doing this function is CoPrime. CoPrime means when two numbers have no common factors other than 1, we call them as CoPrime. For example, I have taken 21 and 22. Okay, first of all, we'll write the factors of 21. Factors of 21 are 1, 3, 7 and 21. Similarly, if you write the factors of 22, it will be 1, then 2, 11 and 22. Now look for the common factor. When you look for the common factor, we can see that only 1 will be there. Only common factor is 1. So common factor is 1, and therefore we can say that therefore 21 and 22 are coprime. All these are the basic terms. Since before going to the main topic, we have to be thorough with these topics. Okay. Now we reach the main topic, that is Euler's Totient function or Phi function. And it was introduced by a Swiss mathematician Leonhard Euler, and it has a deep relationship with prime numbers. And let's see how it works. The totient function of a positive integer where n is greater than 1 is defined as the number of positive integers less than n that are coprime to n. So with the help of example, we can we'll try to understand the concept. Suppose if I take totient of 5. What is the meaning of totient of 5? Number of positive integers less than 5 and coprime to 5. That is the meaning. So which all numbers will come? You can write 1, 2, 3, 4. All these are less than 5 and coprime to it. To it means to the number 5. So how many numbers are there? 4. So that is the meaning. So phi of n is equal to, or here in this case in the example, n takes the value 5. So phi of 5 is equal to 4. So according to the definition, 1, 2, 3, 4, all these are less than 5 and they are coprime to 5. Similarly, you can take any number and try any prime number. 7. If I take 7, so all the numbers positive integers less than 7. So I can write 1, 2, 3, 4, 5, 6. All these are less than 7 and coprime to it. Coprime to 7. So altogether how many numbers are there? 6. So we can write phi 7 is equal, or totient of 7 is equal to 6. Here are some useful properties of Euler's Totient function. The first property is, if P is a prime number, then phi of P, that is totient of P, equal to P minus 1. So if you make use of this property, it will be much easier to solve these type of functions. So let us take phi of 7. 7 is a prime number. So according to this property, it will be 7 minus 1, and that is 6. Similarly, I can take phi of 5. 5 is also a prime number, so it will be 5 minus 1. P is 5, so 4. Let's go to the second property. If m and n are coprime, then phi of mn equal to phi of m into phi of n. So how will you do this one? Suppose if I take totient of 35. Totient of 35, according to this property, I can write it as phi of 7 into 5, right? 7 into 5. So phi of 7 into 7, 5 is 35. 7 and 5 are coprime. Coprime means they have only 1 as common factor. So we can write this as phi of 7 into phi of 5. What is phi of 7? It is 7 minus 1, 6. And what is phi of 5? It is 5 minus 1, 4. So 6 into 4, 24. So the meaning is the number of positive integers less than 35 that are coprime to 35 is 24. Now let us move on to the third property. if n equal to p raised to k, where p is a prime number, then totient of n equal to p raised to k into 1 minus 1 by p. So let's take an example, phi of 625. So we can write this as phi of 5 raised to 4. 5 into 5 into 5 into 5. 5 raised to 4. So according to this property, it is p raised to k. P raised to k is 5 raised to 4 into 1 minus 1 by, what is p here? P is 5. So we can do the simplification. 5 raised to 4 into 1 minus 1 by 5, we can write as 4 by 5. What is 5 raised to 4 by 5? It will be 5 raised to 4 minus 1, 3 into 4. So 125 into 4, we will get as 500. So the meaning is number of positive integers less than 625 that are coprime to 625 is 500. Now next property, fourth one. If n equal to p1 raised to k1, p2 raised to k2, pr raised to kr is the prime factorization of n, then phi of n equal to n into 1 minus 1 by p1 into 1 minus 1 by p2, etc. 1 minus 1 by pr. So we can do one question here. Example, what is totient of 300? So here you can see that we have to do prime factorization of n. So 300 we have to prime factorize. 150, 75, 25, 5. So 300 we can write as, so I have to add that step over here. Prime factorization of 300. How many 2's are there? 2. So 2 raised to 2. How many 3's? Only 1 3. And 2 5's are there. So 5's. 5 raised to 2. So totient of 300 we can write as, according to this property, it is n into. So what is P1, P2, P3, etc.? Those are these numbers. P1 is 2, P2 is 3, and P3 is 5. So we will make use of that. N into, n is 300. So 300 into 1 minus 1 by P1 is 2 into 1 minus 1 by P2 is 3 into 1 minus 1 by P3 is 5. That's it. Now we have to do the simplification. 300 into 1 minus 1 by 2 is 1 by 2. Again, 1 minus 1 by 3 is 2 by 3. And 1 minus 1 by 5 is 4 by 5. So we can do all the simplification. 5 and this will be 60. Then 3 and this will be 20. And 20 into 4 will give you 80. That's it. Now the fifth property. If P and Q are prime, then totient of PQ is equal to P minus 1 into Q minus 1. So here also we can take one example. Phi of, or totient of 21. 21. We know that 21 we can write as 7 into 3. Yeah. So what is P here? P is 7. So 7 minus 1 into, what is Q here? 3. So 3 minus 1. So it will be 6 into 2 and it will be 12.